All right, welcome everyone to today's CDAC webinar, our 152nd webinar in this series on materials in extreme environments. It's my pleasure to introduce today one of our own, Abdul Hasib Manayil Marathamkottil. We call him Abdul. Abdul is a materials chemist who has, over the years, mastered a great many high-pressure diamond anvil cell techniques, including laser heating synthesis, a broad range of X-ray characterization methods, as well as electrical transport techniques and spectroscopic methods. And he's applied these mainly to hydrides, including high-pressure superconducting hydrides, but also a variety of other materials. And most recently, he led an exciting project, took advantage of the upgraded advanced photon source for micron scale X-ray diffraction imaging of superhydrides and megabar pressures, which he'll tell us about today. Abdul also has a lot of experience at other facilities, including facilities at Sandia, at Oak Ridge, at DESY, at Brookhaven, and so on. Abdul received his bachelor's and master's in Mohali, India, where he worked on luminescent liquid crystals. And he was, in fact, the first chemistry graduate student to join our group when we moved in 2019 to UIC. And he just completed his PhD a few months ago and is now a postdoc in CDAC at UIC. So over to you, Abdul. Glad to welcome you, and thanks for agreeing to give this talk.
Thank you. Hello, everyone. Thank you for the invitation to present the CDAC webinar. Thank you, Russ, for the kind introduction, very long. Today, I'll be talking about our recent work on high TC hydrate superconductors, specifically how new imaging methods at megabar pressures are helping us understand what's actually happening inside these materials at the micron scale. I'll start with a brief introduction to set the stage and then move into the results. Let me start with the basics for those who may be coming from outside the field. Superconductivity is a quantum state of matter with two defining properties. First, zero electrical resistance. Below a critical temperature Tc, resistance drops to exactly zero. Resistance drops to exactly zero. Current flows indefinitely with no energy loss whatsoever. Second, the Mason effect. A superconductor expels all magnetic fields from its interior. This is not just as a consequence of zero resistance, it is a fundamental different thermodynamic state. We already use this superconductivity in MRI machines, particle accelerators like the Large Hadron Collider at CERN and experimental maglev trains. But all of these require cooling to liquid helium temperatures. Room temperature superconductivity would be transformative. It would change how we generate, transmit, and store energy. It would revolutionize medicine and computing. That is the grand challenge driving this field. We have seen what superconductivity is and why room temperature superconductivity would be transformative. So how do we actually get there? This timeline tells a story spanning over a century, but the real acceleration happened in the last decade, and it started with a theoretical idea. The foundation goes back to the 1930s when it was first proposed that under extreme pressure, hydrogen would form a metallic lattice, behave like an alkali metal metallic hydrogen. Ashcroft connected this to the superconductivity in around 1968, applying BCS theory. He argued that metallic hydrogen, because of its uniquely light mass and strong electron-photon coupling, should be an exceptionally high temperature superconductor, potentially at or above room temperature. The obstacle was obvious. Stabilizing metallic hydrogen requires pressures above 400 GPa. For context, 1 GPa is about 10,000 atmospheres. 400 GPa remain beyond reliable experimental reach till now. In 2004, Ashcroft made a second equally important proposal. Instead of metallizing hydrogen directly, embedded it in a metal lattice. Heavier atoms could provide what he called chemical precompression, squeezing hydrogen electronically and structurally, mimicking the condition needed for metallization. but at far more accessible pressures. This single idea sparked a renaissance in hydride research. Over the theoretical side, crystal structure prediction algorithms like USPEC's Calypso allowed systematic screening of hydrogen-rich compounds before anyone synthesized them. Theory was now guiding experiment. The results followed quickly. In 2015, H3S reached 203 Kelvin at 155 GPa, the first hydride to break 200 Kelvin. The first experimental proof of Ashcroft vision as well. Then in 2018, LH10 reached 260 Kelvin at 188 GPa, the highest reproducible TC ever measured, and the benchmark that defines the modern field. And after 2020, you can see the scatter plot explode here. That is the externary hydride era, which we will come back to. But this raises the question: what is it about the metal hydride structure, physically and chemically, that make it so effective? That is exactly what next slide here. The answer is in the BCS equation, which is on the top here. The TC scales with the two quantities: the Debye temperature theta d, which reflects phonon frequencies, and the electron-phonon coupling, constant lambda. And to maximize TC, you want both as large as possible. Now consider hydrogen. It has the lowest atomic mass of any element, just one atomic mass unit. Phonon frequency scales as 1 over the square root of mass. So hydrogen gives the highest phonon frequencies and therefore the highest Debye temperature of any element, around 3500 Kelvin. Nothing else comes close. That directly maximizes the first term in the BCS equation. But pure metallic hydrogen, as we just saw, needed around more than 400 GPa. So the question becomes, how do you get atomic hydrogen at manageable pressures? So this is where the molecular orbital diagram becomes important. When a metal atom like lanthanum sits adjacent to hydrogen, it donates electrons into the H2 antibonding sigma orbital and at the high pressures in the metal hydride. This weakens and eventually breaks the hydrogen bond chemically without mechanical compression. Hydrogen is dissociated into an atomic form without needing the 400 GPa. That is a chemical pre-compression acting at the electronic level. The dissociated hydrogen doesn't just sit randomly. It self-organizes into the extended three-dimensional networks, clathrate cage structures. In LH10, we have a 32 hydrogen atom form a cage around each lanthanum atom. The hydrogen distance inside these cages are approximately around 1.1 angstrom, remarkably close to what is predicted for atomic metallic hydrogen. The consequence for superconductivity is direct. The high phonon frequencies are preserved, and because hydrogen is still light and atomic, electron-phonon coupling lambda is strong, around 3.4 in LH10, because the dense hydrogen network creates a high electronic density of states at the Fermi level. Both variables in the BCS equations are maximized. The result, TC above 250 Kelvin at megabar pressures, room temperatures within the site, but only at extreme pressures, which raises the next question: can we do better? So room temperature is within sight, but only at extreme pressures. Can we do better? The answer that, and to answer that, let's look at the two structures on the left here. These are the two key binary clathrate frameworks that define the field. One on the left, the H32 cage of cubic Fo-3m LH10, a 32 hydrogen atom surrounding each lanthanum, which I mentioned before, the structure behind the 260 Kelvin record. On the right, the H29 cage, a cage of hexagonal P63 MMC YH9, a slightly different geometry with a TC of 243 Kelvin at 201 GPa. These two structures represent two endpoints of design space. LH10 gives the highest TC but requires nearly 200 GPa, and the YH10 is theoretically predicted to reach about 300 Kelvin but has never been realized experimentally till yet, partially because it requires even high pressures. And both binary systems have no tuning knobs. You get what you get from the chemistry. This is where ternary hydride comes in. The idea is straightforward: introduce a third element to create new degrees of freedom. Chemical substitution let you simultaneously tune the electron-phonon coupling, shift the synthesis pressure, and extend the pressure range over which the cage structure remains stable. Theory led the way here. Calculations showed that allowing rare earth elements preserve the clathrate cage while modifying the phonon spectrum, potentially pushing the TC higher. Experiments followed rapidly. Look at the chart from here. From 2015 to 2020, the field was dominated by binary hydrates such as the H3S, LH10, YH6. Then after 2021, the chart explodes. Almost every new entry is a ternary or a multi-component system, such as the LaYH10, lanthanum cerium hydrates, lanthanum scandium hydrates, and even yttrium sulfur hydrate, and more. The pace of discovery accelerated dramatically in the last 5 to 6 years. And at the top of the chart, the lanthanum scandium 2 and H24, this system has been reported with the TC approaching room temperature, around 2898 Kelvin. This shows how fast this field is moving and how far chemical complexity can take us. Binary hydrates gave the proof of concept. Ternary hydrates are where the real exploration is happening now, and that is exactly where our work sits as well. In binary hydrates established the records. Ternary hydrates are expanding the landscape, but to make real progress, we need to confront what makes this field experimentally hard. First, megabar pressure barrier. The highest TC hydrates require pressures above 150 GPa. This is equivalent to 1.5 million atmospheres, accessible only in diamond anvil cells with samples roughly 30 micron across. Not scalable, but the science is real. The second, phase heterogeneity. Most synthesis produces multiple coexisting structural phases in the same tiny sample. Bulk transport measurements average over all of them, so you can't tell which phase is driving which transition. And the third, validation and reproducibility. Extreme conditions and complex chemistry makes independent verification genuinely difficult. The field has faced serious scrutiny on this front. And fourth, no ambient pressure analog. Clathrate cage structures are metastable below 100 GPa. Recovery paths are largely unexplored. We are slowly tapping into it with recent advancements in pressure quenching protocols. These were the 4 challenges that shaped my thesis. My objectives were to address all of them, synthesizing the lanthanum-based ternary hydrates to chemically tune these systems, mapping their structure at the micron scale, directly linked in the structure physical property correlation, and developing a new non-contact spectroscopic probes. Today, I will focus on 2 different systems, a lanthanum yttrium hydrogen system, where we simultaneously pursued chemical tuning as well as the X-ray diffraction imaging. And another system I'm going to talk about is the lanthanum aluminum hydrogen system, where we used IR spectroscopic for superconducting gap. The talk outline, we've just finished. We'll go through the introduction, then go to LaYH10, then go to LaH10. So, since we have established why hydrates are promising and why the ternary strategy makes sense, let me set the stage for the first project by framing the central problem. The question we address is, how do microscopic structural domains govern macroscopic superconducting behavior? And for the first time in any hydrate, we have a direct spatial answer. But first, why is this question so hard to answer with conventional measurements? Look at the resistance versus temperature curve from the calcium hydrate system at 165 GPa. Instead of one sharp drop to 0, you see multiple distinct steps, broad, overlapping transitions spanning tens of Kelvin. This kind of behavior is ubiquitous across binary and ternary hydrates. The standard interpretation has always been structural heterogeneity, different structural phases coexisting in the same sample, each with its own TC, each contributing to measured resistance signal. And there is indirect evidence for this. So when you change each electrode you use as a current and voltage probes on the same sample, you get completely different transition shapes, sharp, broad, or multi-step, depending on which spatial path the current takes through the sample. But that indirect evidence is all the field has had. No hydrate study had ever directly proven which structural domain drives which transition temperature. This spatial link between the structure and transport had never been established. So that is exactly the missing piece this work provides by combining micron scale X-ray phase imaging with spatially resolved resistance measurements on the same sample at the same pressure conditions. So we established the problem. phase heterogeneity obscures the physics, and no hydrogen study had directly linked structural domains to the superconducting transitions. So the question is, which system do you use to solve it? The choice has to be deliberate. You need a system where the chemistry is well motivated, the theory makes a clear prediction, and the experimental conditions are favorable for the imaging methodology. For us, that system was lanthanum yttrium H10. The logic starts here. On the left, LH10 is the benchmark at 260 Kelvin at 188 GPa. The YH10 is theoretically predicted to reach above 300 Kelvin in TC, but has never been realized experimentally. So yttrium is lighter than lanthanum, which means a higher phonon frequencies, the triangle diagram captures this. By alloying lanthanum and yttrium with hydrogen, we are exploring the composition space between two known endpoints, trying to combine lanthanum's experimental stability with yttrium's predicted phonon advantage. Theory confirms this works. This strategy, and the Kusurava and colleagues predicted that a LaYH10 salt solutions are thermodynamically stable. The yttrium substitution preserved the Cartwright framework, and that TC rises Y with yttrium content toward the YH10 limit. But the most important reason we can choose this system came from our own experiments. When we initially synthesized LaYH10, we observed structural heterogeneity, multiple phases coexisting within the same sample chamber. So rather than treating this as a complication, we recognized it as an opportunity. So one system, two objectives. The structural heterogeneity that makes bulk property ambiguous is exactly what makes the system ideal test bed, giving us a distinct domains to image and distinct transition to assign. So, and if the ternary strategy works as a theory predicts, we get a lower synthesis pressure and extended stability as a bonus. With that motivation established, let me show how the sample is actually made. So here's how the sample is actually made. We start with an alloy arc melted at Ames laboratory from high purity lanthanum and yttrium under argon. SCM EDS confirmed a homogeneous single phase alloy. So we are working with a clean, well characterized precursor before we even enter the DAC. So on the left, you can see a schematic DAC assembly. The two opposing diamonds, the gasket and the electrical leads coming in the from the sides. The image panel works through the actual sample preparation stages. The first panel shows the sample chamber. The final panel shows what the sample chamber looks after loading. The lanthanum yttrium alloy sitting in direct contact with ammonia borane with the platinum electrodes. It's shown here. For the transport DAC, gasket preparation is critical. We pre-fill a rhenium gasket with an insulating layer. We use a cubic boron nitride and epoxy mixture. Then laser drill at the sample and the center for the sample chamber. This electrically insulates the chamber from the gasket, essentially for the 4-pore measurements I will show later. 4 platinum electrodes about 2 micron thick are manually positioned on the diamond culet, as you can see here in a Van der Pol geometry. The hydrogen source is ammonia borane NH3BH3, which decomposes above 773 Kelvin to release hydrogen. It also serves as the pressure transmitting medium. We compress to 158 GPa in multiple steps, collecting the XRD at intermediate pressures to track the structural evolution of the alloy. Laser heating is performed at the 16 IDV and 13 IDD of advanced photon source at Argonne National Lab. And you can see the experimental setup here. The synchronous X-ray beams is coming across through the DAC, and along with that, laser also heats the sample from one side, or we can do both sides as well. We deliver around 300 millisecond pulses, reaching estimated temperatures between 200 and 1800 Kelvin at the metal ammonia borane interface. And here is what the XRD tells us before and after heating. The black pattern is the in the bottom is the lanthanum 0.9 yttrium 0.1 alloy at 158 GPa. You can see the distorted cubic FMM alloy structure from the XRD along with the platinum electrodes reflections marked explicitly. So after laser heating, the red pattern, those alloy peaks are completely gone, and we have something new. So this gives us that the synthesis is worked, and importantly, it is reproducible. we ran multiple independent syntheses and obtained the same result. So what actually formed? This is the Lebel refinement of the diffraction pattern at 153 gigapascals. The red curve is the observed data, the black is the calculated fit, and the gray below is the residual. And answer is two phases simultaneously. The dominant reflections index to the cubic F-3m structure, the same structure as pure LAH10, with the lattice parameters of around 5.115 angstroms and a unicell volume of 136 cubic angstroms. We also clearly see a second phase of a second set of reflections belonging to the hexagonal PC3 MMC structure here with a volume of 66.1 cubic angstroms. Now here is a key structure evidence for yttrium incorporation. If we plot the unicell volume against pressure, the PV curve on the right here, our LaH10 volume sits systematically below those of undoped LaH10 from the literature. So that slight lattice contraction is exactly what you expect from roughly 10% substitution of the larger lanthanum atom with a smaller yttrium atom. And the stoichiometry analysis confirms approximately 10 hydrogen atoms per metal atom for both phases, consistent with the nominal composition. The second important finding from the structural data is phase stability. Both cubic and hexagonal phases survive decompression all the way down to 136 GPa. So the pure LH10 is usually typically transforms to a C2 bar M or R minus 3M around 150 GPa. We can see that both our FCC and the LHCP, lanthanum yttrium H10, stable up to the 136 GPa. So this is going to be important when we look at the transport data next. So we know we have two phases coexisting, but what are they spatially? So this is where the scanning X-ray diffraction microscopy or XSDM comes in. Thanks to the APSU upgrade, the beam at HP CAT beamline 16 IDB was reduced from roughly 20 square microns down to 2 square microns, with dramatically improved brilliance and minimal beam tails. That is different between seeing blobs and seeing actual domain structure. The workflow is shown on the left here. We raster scan across the focus X-ray beam across sample on a 11 into 11 grid with steps of 2 to 3 microns. At each point, we collect a full 2D X-ray diffraction pattern. The XDI software then integrates the intensity within the user-defined 2 theta windows that's specific to each phase and assembles those integrated intensities into a 2-dimensional spatial map. The maps at the 150 GPa and 136 GPa are shown here. The red is the cubic F-3m phase and the blue is the P63 MMC phase. The cubic phase covers about 42% of the sample space, and the it's like a clusters around the pockets in a pockets near the electrode 1 and L2. And which is where also we had excess ammonia borane, and as well as the higher hydrogen availability was available during that during the laser heating. The hexagonal phase, where it's in blue color, has like remaining for 58%, and is a more of look like a continuous matrix across the sample. And local hydrogen content and the laser heating geometry appear to drive these phase boundaries. So this this spatial map, the spatial map is the foundation for everything that follows in the next few slides. So with the phase map in hand, we can now look at the transport data. The setup is a 4-probe DC resistance measurement in Van der Pol configuration, shown schematically on the left. 4-probe geometry eliminates contact resistance, which is critical when your sample is only about 30 micron across. We use a current source at 0.1 milliamps and a nanovoltmeter and switching matrix to cycle through multiple current and voltage probe permutations. All data shown are here from warming cycle at roughly 1 Kelvin per minute, where thermal gradients are minimized. The Van der Pol method was originally designed for homogeneous thin films, but we have adapted it here for inhomogeneous multi-phase DAC sample. We collect 8 partial configurations which is like RABCD, where the voltage is taken across V and C and D, and the current is going across A and B. And here we are plotting a four probe average four probe resistance with this equation shown here, and the results at the 150. The results at the 153 GPa are shown here. Two distinct transitions are clearly visible. The first drops at 244 Kelvin, and the second transition near 220 Kelvin before the resistance reaches zero. So the total transition width is roughly 28 Kelvin here, unusually broad for a DC transport, and characteristics of phase coexistence and electronic heterogeneity. So two transitions, two structural phases, and the next step is making the direct connection. So before making the direct connection, let me show two additional pieces of evidence that these transitions are robust. On the left, resistance versus temperature at 4 pressures from 153 GPa to 136 GPa. The two-step transition is consistently present across the entire decompression range. So the persistence confirms we are not seeing a transient artifact. On the right, we have a current voltage measurement at 146 GPa. About TC, the IV relationship is perfectly linear, ohmic, as expected for a normal metal. As we cool down to 230 Kelvin, the curve becomes non-linear, non-ohmic, with a voltage suppressed near zero current. This non-ohmic IV behavior is the hallmark signature of a superconducting state, ruling out any artifacts. The question remains which phase owns which transition. That is now answerable we can have an answer now. So this is the central results of the LAY H10 work, and I want to walk through it carefully because it demonstrates the full power of combining structural imaging with spatially resolved transport. We take each of the 8 partial resistance configurations, RABCD, defined as the voltage across C and D, and the divided by the current to go through A and B, and overlay this current path directly onto the XDI phase map, which we got from the SSDM combined with SDI software. So this tells us exactly which structural domain each measurement is sampling. Look at the panel at the left, the R1, 2, 3, 4. Current flows from electrode 1 and 2, and the voltage sensor across 3 and 4. The voltage path spans across the a mixed phase across the both red and blue regions. It is sampling a mixed phase territory, and the partial resistance reflects exactly that. A broad two-step transition with onset around 241 Kelvin and a 218 Kelvin. You are seeing and the total width around 20 Kelvin. So you are seeing the both phases contributing to the partial resistance simultaneously. Now look at the right. The R3 for R3 4 1 2. The current flows through the 3 and 4, and the voltage is sensed across electrodes 1 and 2. The voltage path sits preferentially in a cubic heavy majority region around the near electrode 2, where the red domains are concentrated. In the partial resistance shows like a sharp and single step transition at 240 Kelvin with very narrow width under 10 Kelvin. So one phase, one transition, one clean drop. So the assignment is then the phase assignment or like it's unambiguous for the which transition is correspond to which phase. So the cubic phase drives the higher temperature transition near to 44 Kelvin, and the hexagonal phase is responsible for the lower one near 220 Kelvin. The both transition seen in bulk measurements arise simply from sampling both phases simultaneously. No previous study on any hydrate had ever established a direct spatial correspondence between specific crystal structure and a specific TC. So this is the first direct demonstration that micron scale structural domains govern distinct superconducting transition in any hydrate. And this technique or this method established a new methodology for studying mixed phase superconductors under extreme conditions. So to summarize LAY-H10 work in 4 points. First, phase coexistence is established by yttrium substitution. That 10% yttrium incorporation promotes coexistence of cubic and hexagonal clathrate phases from 168 GPa down to 136 gigapascals, well below the stability limit for pure LAH10. And the second, the APS-C upgrade enabled the first micron scale phase imaging in any in a superhydride at megabar pressures. The cubic phase clusters near the hydrogen source and the hexagonal phase form a continuous matrix. The third, two distinct superconducting transitions to around 244 Kelvin for the 240 and 220 Kelvin persistent across the full pressure range. Both are slightly suppressed relative to pure LH10. And the fourth, the highlight, this is the first direct proof that the domain at the domain level that local structural phases govern distinct superconducting transition in any hydrate, not inferred, not averaged, directly mapped. So looking forward, an exciting next step is combining XSDM and transport with Mason effect imaging to map a superconducting volume fraction directly and complete the picture from both transport and magnetic standpoint. Now, that's kind of concludes the LA story, but you may be familiar with how Apple structures their iPhone launches. So you usually always have one more thing. So I also have one more thing, and so the LAYH10 work required a specific DAC configuration, platinum electrodes, insulated gasket, transport measurements. That configuration takes significant preparation time, and not every synthesis runs includes it. So here is the situation with lanthanum aluminum H10. We synthesize this sample at 172 gigapascals. The optical image on the left shows a clean sample region after laser heating. The singleton XRD on the right confirms what we have made. It is a well-characterized sample, and the structural identity is secure. But this DAC has no electrodes, no coils for magnetic measurements, and tunneling spectroscopy and ARPAS are out of this question at these pressures and sample sizes. So how do you probe the superconducting state in a sample where every contact method is unavailable? The answer is infrared refractivity through the diamond anvil cell itself. So this is a completely non-contact optical measurement. The diamond is transparent in the infrared region, and the superconducting gap has a direct, well-defined optical signature that you can measure without touching the sample at all. So that is what the next few slides are about. So let me explain the physics before showing the data. So in BCS superconductivity, breaking a copper pair caused a minimum energy of 2 delta, the superconducting gap. This has a direct optical consequence. Photons below 2 delta cannot break pairs and are perfectly reflected. Photons above 2 delta breaks copper pairs and are absorbed. Reflectivity drops sharply. So the diagram on the right shows this. So look at the red curve. The superconducting state, refractivity states at unity up to the gap edge at the 2 delta, then falls rapidly. The blue curve is the normal state, has no such future. It just declines gradually with no sharp edge anywhere. So when the sample goes on superconducting on cooling, this is what we expect to see: reflectivity building up below the gap energy and dropping above it. The sharp crossover is a spectroscopic fingerprint we are hunting for. And it gives us a superconducting signature without a single electrical contact. This approach was previously demonstrated on a sulfur hydrate, validating this technique on hydrogen dominant superconductor. So what we are doing here is extending into a clathrate hydrate, opening a new optical window into this entire family of high TC materials. So the measurement was performed at beamline 22 IR1. The FI is beamline at NSLS2 Brookhaven, and then geometry of the measurement is shown here. So the infrared beam enters through the diamond, and we cut 2 intensities sequentially. First, IAD. This is the intensity from the air diamond interface. This is our reference, and it depends only on the diamond's refractive index. And the second, the IDS. This is the intensity reflected from the diamond and the sample surface. This signals that carries the information about the sample. So taking the ratio IDS or IAD cancels common factors like source intensity and detector efficiency, and with a non-diamond refractive index of 2.42, we can extract the absolute reflectance of the sample. But there's a practical complication. The diamond has a wavelength dependent absorption that is difficult to determine precisely at high pressures. So rather than trying to correct for it exactly, we take a simple approach. We compute the relative reflectance. So RT over RT(N), the ratio of the sample reflectance at temperature T to the reflectance at a normal state reference temperature well above Tc. So because of the eta of lambda is the same at both temperatures, it cancels out and completely in the ratio. So what remains is purely the temperature driven change in the sample's optical response, which is exactly what we are after. So the raw data on the right here shows that IDS over IAD versus photon energy from 100 MeV to 175 MeV at temperatures from 297 Kelvin to 100 Kelvin. Already in the raw signal, you can see this trend below 130 MeV. The ratio increases systematically as temperature decreases. The sample is becoming more reflective in the far infrared as it cools. So this is a hint of what's happening, and that next slide shows it clearly. So now here is normalized data, and this is where the physics become clear. On the left, here we have RT over the reflectance as a specific temperature versus room temperature versus phonon over room temperature versus phonon energy for the lanthanum aluminum H10 at around 172 GPa at temperatures from 260 to 100 Kelvin. As we cool down to 230 Kelvin and below, we can see a distinctive shape develops. If you can see, similar to what we see from the in the theoretical or like in a ideal superconductor. The ratio rises below 130 MeV and fall below 130 MeV and falls below falls above that energy. So by 100 Kelvin, the enhancement in the lower energy region is roughly a factor of 2 to that of 260 Kelvin reference. So this behavior is consistent with the suppression of optical absorption below the superconducting gap. As Cooper form, the optical excitation below 2 delta is 2 delta are blocked, and the reflectivity build up in that energy window. See on the right, the theoretical IR reflectivity prediction for LH10 are calculated using the DFT plus LH plus theory for TC of 230 Kelvin at 210 GPa. The calculation shows the same characteristics, shape, reflectance rising at a low energy and below 2 delta and falling above with the onset near 100 MeV. So our data mirrors this trend closely. The same onset energy, the same direction of spectral weight redistribution, and the same progress evolution with decreasing temperature. Together, this constitutes a strong spectroscopic evidence for superconductivity in the lanthanum aluminum H10 and the first synchrotron IR reflectivity measurement on a class-A superhydrate. So the LH10 results give us three things. First, synthesis. We have confirmed the first cubic Fm-3m lanthanum aluminum H10 cladrate. The cubic phase forms at pressures of 165 GPa and above, and that's an important practical finding for future studies targeting the system. And the second, the transport, the two resistance drops approximately around 240 Kelvin for cubic systems and at around 227 Kelvin for the hexagonal phases. And the third, the methodological contribution, the IR reflectivity data shows that classical optical signature of a superconducting gap around 130 MeV. The spectral weight redistribution below 2 delta mirrors the LH10 theoretical prediction. Looking forward, this opens the door to a fully quantitative optical probe of superconducting gap across the entire cladrate hydride family. So I want to close this scientific content with a takeaway message on this slide. So we have shown that synchrotron X-ray diffraction, imaging, and spatially resolved transport can establish a direct, unambiguous link between micron scale structure domains and distinct superconducting transitions. It answers a question that has been implicit in the field for years. When you see a broad or stepped resistance curve in a superconductor, what exactly is each feature is telling you? Now we can answer that at the domain level. And we have shown that when transport is unavailable, infrared reflectivity through the diamond envelope is a viable path to probing the superconducting state. Together, these two methods represent a meaningful step forward in our experimental toolkit for studying these materials under extreme conditions. The LAYS10 work is published in Open Access and Natural Communications. You can see the reference here. I hope you can go through it and get a full story of the what I'm told went through today. So I would like to thank the people who made this work possible at UIC, Nilesh, Kui, Nutar, Alik, Liu, Stephen, obviously Russ for the all the they are all part of the expense analysis and as for guidance throughout my PhD and now the postdoc. At Argan, Rose and Zulu and Stella and Vitali. With that, thank you very much for listening and talk.
Thank you very much, Abdul, for a very nice talk. It's now open for questions and comments. I see a lot of clapped hands. That's great. So please unmute yourself or just speak up or put your comment in chat. So
Hi,
go ahead.
Abdul. Oh,
Roma, go
sorry.
ahead.
Thanks. Hi, Abdul. Great talk. It's really exciting to see you broadening your research since grad school. I was just wondering, what advice would you give to a new student who is looking to take on this really challenging research that you've been doing?
I think with high rate research, especially like above megabar, never give up. Your time will come.
It's great advice.
One day the material will superconduct.
Awesome. Well, great job. Really happy to see your work.
Thank you.
Sure. Oh, awesome.
Yeah, go ahead.
That's I think who someone's having a question. He's raising the hand first.
Okay, let me see.
Who's that? Yeah, that's
it's fine. You can go first. It's okay.
Oh, thanks. Hi, Abdul. That's a very great talk, and I learned a lot. But I want to take a look at the page 9. That's the setup thing. Can I?
Yeah.
Yeah. So like you don't have any Ruby inside the deck. How do you measure the pressure of this entire setup?
So we do two in two mesh space. First is we do diamond edge. Then the second one we use the platinum as the pressure standard as well from the leads.
Oh,
and we can also get
Oh, okay.
So we use that both as a standard for the pressure.
Mm-hmm. And then for the electrical lead on the electrical lead, that these things, and under the like high pressure, this extremely high pressure, and will the lead deform and change the shape because it's too much compression for them as well?
We are using like a 2 micron thick platinum foils, so we don't see much changes with in our experiments. We had used like multiple techniques before, with the PVD, FIB, and etc. So we see better results with the hand placed platinum foils, like a 2 micron thick foils.
Yes. Yep. And one more question in this page, I want to ask about the reaction itself. So it looks like the hydrogen gas, the source is coming from that reaction, right?
Yeah.
NH3 BH3, and then it decomposes. But this decomposition is also occurring under the high pressure, right?
So there is multiple studies on the ammonia borane and how that's dissociates into hydrogen as well as three steps. So temperature can drive it, and a little bit of pressure also can drive it. So what we see with in our experiments, like from experience, that if we keep the ammonia borane like below 60 GPa, it start making the H3 phases with the lanthanum. So what we usually after loading, we immediately go past the 50 GPa to avoid the formation of the lower hydrates.
Okay.
That's how we jump that.
I just feel a little. I just feel a little worried because under the high pressure, extremely high pressure, and then the reaction itself is generating the gas. So actually, in the equilibrium, Le Chatelet principle, right? When there's a external high pressure and then you're generating the gas, it's actually suppressed. That's the thing I'm worrying about. Yeah, it doesn't have any kind of trouble. Like the gas will still come out when you heat it or something.
I think using ammonia borane is pretty established in this for the lanthanum like hydrate use. We didn't see any issue with that. Maybe in the high pressure the chemistry is completely different.
Okay.
Russ mentions like we have a completely different periodic table under high pressure. So yeah, maybe the science is a bit different under high pressure.
Yeah, that makes sense. Yeah, thanks very much. Yeah.
I would say that it was a real breakthrough in the late 70s when hydrogen gas was compressed and contained in a diamond cell. People thought it wouldn't happen, but you can actually seal the gas and form the high pressure solid and multiple solid phases. It makes a very good seal, even for hydrogen and helium and other light gases. So Hussam and then Laszlo.
Hi, Abdul. Great
Hey.
talk.
Yep.
Just kind of a general question. You spent a lot of time talking about how these systems are really kind of like perfected to study for superconductors with the composition and the light elements using hydrogen. So why is it that we need to use such high pressures to get to these superconducting temperatures? Like, why is that much pressure needed to get to a TC?
Here it's more about we are getting the decahydrate phases, and which is in the cage is like closer to metallic hydrogen. So as I mentioned in the earlier stage, if you want some metallic hydrogen is like ready to be at the room temperature superconductor, but we need a very high temperature, high pressure. But with the metallic hydrates, we can get it near accessible pressures with the DAC, and that kind of mimics the metallic hydrogen structure. So that's the idea behind using the decent pressure, not very extreme, but still extreme pressure.
So in other words, you need this high pressure to break up the hydrogen molecules. And you made the point that that is accommodated via this pre-compression idea that was proposed by Ashcroft, right?
Yep.
Okay, Laszlo.
Yes, Abdul, a very nice presentation. Congratulations.
Thank you.
And very courageous measurements, especially the optical measurements, I know something about that in BISCO high TC at ambient pressure. So in your deck, what is the diffraction limit? So because that's why I think the data are less, I would say, convincing than in a classical superconductor you would expect, right?
Yes, I did calculate that. I don't know the exact number, but that's why I cut off the. We can go with much lower in energy. That's why I cut off that around 100 MeV for my data, because around 760 MeV with our opening for the DAC is much smaller. Like it's around CT is like around 60 micron opening.
Because 130 MeV, it's roughly 1,000 wave numbers, right?
Yeah.
So you see that this shoulder, the break at 1,000 wave numbers, right?
Yep.
Yes.
Yeah.
Yes.
Yeah, we are planning to do this with some other systems with around 100 GPa, so we can have a bit more bigger openings to get like a bit more aperture as well. Yeah,
Yes.
the question is exactly correct. We know. Yeah, we are kind of
Yes, because in the below the gap energy, you would expect total reflectance, right? 100% reflectivity.
Yeah, but that's not possible in DAX because of the low.
Yes, in DAX. Yes, with all the piece around. But I would say that the data are promising. I wouldn't say that they are convincing, but promising.
that we are also on that same.
So if you put the gap energy at 130 MeV, it's in the weak coupling limit or it's a high coupling limit? The superconductivity. So it's the 2 delta is 3.5
Yeah,
kBTC or
this is the decoupling, because there's one more, should be somewhere around 400 region, right? So yeah, this is, I think, the decoupling limit.
yes. Anyhow, I mean, these are, I mean, very nice, promising data. Absolutely. And once again, congratulations.
Thank you. Yeah, we are going back with the other systems, which is like at lower pressure, to try to do it with a bit more.
So you measure it with Larry Carr or with Chris Holmes? So who is
With Zanjal Liu.
who?
With Liu at FIS.
Okay. I don't know.
Yeah,
Okay.
he's our beamline scientist at FIS. So we work with Larry. Larry is the cognizant beamline scientist at NSLS. So Laszlo goes back to the very beginning when we were working at U2A back in the 90s. So great comment. So Abdul, why don't you go back to your picture of the sample, because it's quite clear that you have a diffraction limit there. So that sample size there defines your diffraction limit.
Yes.
So it's really, it's on the order of 20 microns or something like that, right?
Yeah, it's like 20, 21.
So this is not an ideal sample for IR reflectivity, but it was one that was available. So we're continuing to work on this.
This is the only way to measure the gap, right? Gap energy, because tunneling is impossible, I think. So just optical measurements could give us idea about the gap value, right?
Yeah.
Okay, more comments or questions? Okay, if not, let's thank Abdul for a very nice talk, and thank you all for joining us.
Thank you. Thanks for the opportunity.